Okay, welcome back. So last time we discussed congruent numbers. So a positive integer n is a congruent number if n is the area of a right angle triangle with all three sides of rational length. That is, there exists an n in n. So n in n is a congruent number if there are a, b, c rational numbers and positive rationals because they represent length of a. So this I've just denoted q greater than 0 is the shorthand notation for positive rationals, such that half AB equal to n, so the area of the triangle is n, and a square plus b square is c square. As I mentioned, the 3 is in q is important condition here. So we saw example like 6 is a congruent number because 4 half into 4 into 3 is 6. 5 is a congruent number because half into 20 by 3 into 3 by 2 is 5. And half into 24 by 5 and 35 by 12 is 7. So these are congruent numbers. So question is which positive square free integers are congruent numbers? And so one of the question is that, and we discussed briefly about it, and we'll discuss more about it today. So one caution was that 34 is also a congruent number. So conjecture was that any integer which leaves the remainder 5, 6, or 7 modulo 8 is a congruent number. And but these are not all congruent numbers. So we saw example of 5, 6, and 7, and this is a part of a bigger phenomena conjecturally, and this is not resolved that 5 mod 8, 6 mod 8, and 7 mod 8, any such integer is a congruent number. But it's not if and only if there are integers like 2 mod 8 which can also be congruent. And one thing was the scaling. So it's better to talk about square free positive integers when talking about congruent number because 34, for example, is a congruent number, and 34 is scaling is important because d square, if n is a congruent number, if and only if d square n is a congruent number for any d in z, and d is not equal to 0. So one of the key theorem we discussed last time is 1 is not a congruent number. Okay, and this is via the method of infinite descent due to Fermat. If 1 is a congruent number, then there exists a, b, c, d in n, so that a square plus b square equals c square and a b equals 2b square. 1 being congruent number is equivalent to any d. D in n, d square is a congruent number. So yeah, there will be a, b, c, d in natural numbers, so that a square plus b square is c square and a b equal to 2b square. And in fact, we can assume GCD of AB equal to 1. And then we constructed another Pythagorean triplet A square, triple A square plus B square equal to A prime square plus B prime square equal to C prime square. A prime B prime is 2D prime square, and GCD of A prime B prime is 1, such that C prime is less than C. So this is the process of infinite descent. So starting with C, we got another positive integer c prime, so the c prime is triple less than c, and this process can be continued infinitely, and that's like a infinite descent, which is not possible because any subset of natural is the least element. So if you look at this triangle, then if there is a side of so there's a triangle with length c, and inside that we can put an integer triangle of length c prime and then c double prime, and this can be apparently continued infinitely, which is never possible. And the technical key idea was used as the variation is the fact that z is a UFD, and if product of two integers is a square and they're co-prime to each other, then each of them must be square. So this is the idea which was used, and yeah. And in the process, we almost kind of see that x to the w to the power 4 minus t to the power 4 equal to y square has no integer solutions. Although, so that gives rise to the fact that in particular x to the power 4 plus y to the power 4 equal to z to the power 4 has no solutions, because if there is a solution of x to the power 4 plus y to the power 4 equal to z to the power 4, so no solution meaning any solution satisfied x, y, z equal to 0. Product of them equal to 0, so at least one of them has to be 0. If one of them is 0, then you can sort of work out what are the possibilities, like 1, 0, 1, those kind of 1, 0, 1 or minus 1, 0, 1, that kind of possibility. So if this is a solution, then if you put z square equal to u, then x to the power 4 plus y to the power 4 equal to u square also as a solution. That will contradict the previous one. Okay. So in the sense that solution, then x, y, u will be 0. So x, y, and z square will be 0. So then x, y, z also has to be 0 because these are all integers you are talking. So this corollary followed from the previous corollary. And as I said, this was the special case of Fermat's last theorem, that if x n greater than 0, then x to the power n plus y to the power n equal to z to the power n. X, y, and z is only possible when product of x, y, z is 0. Okay. And this was proved by Wise, along with many with the helping input or important ingredients from many people almost 350 years after Fermat conjecture. But when Fermat conjecture, he only had this proven in some sense this, and this was the only written evidence he had for this conjecture. And the proof of the Fermat's last theorem uses important ingredients, which itself became an important part of mathematics. Okay, so and we saw some applications. So today, let us do some exercises before going to the other results. So, for example, calculate the discriminant of the binary quadratic forms. 3xy minus 5. First exercise is 3xy minus 5y square and 5xy minus 3y square. Okay. The binary quadratic forms. Calculate the discriminant. Okay, so here the binary quadratic form has a equal to 0, b equal to 3, and c equal to minus 5. So it is not in reduced form. And here b square minus 4ac is the discriminant. So the discriminant delta, sorry, and here delta discriminant is given by b square minus 4ac. So it is 9 minus 4 into 0 into minus 5. So it's just 9. And it is 5xy minus 3y squared. So a is equal to 0 again, b is 5, and c is minus 3. So again, it is not in reduced form, but nonetheless, the discriminant we can calculate. So let's just say xy, xy to this, gxy to this, delta f, this delta g, delta g. So this is again b square minus 4ac, but b is 5 and again a is 0, so it's just 25. So these are primitive forms, these are integral forms, these are primitive form, but these are not positive definite. Okay? Discriminant is positive. This one easy exercise almost follows from the definition. Let us do some other exercises. So calculate the discriminant of the following quadratic fields. One is q square root of minus 1, 1, 1, and the second is q square root of minus 1, 3. So for the first one, q square root of minus 1, 1, 1, you recall that minus 1, 1 is, you write minus 1, 1 equal to minus 1, 1, 12 plus 1, and minus 1, 1, 12 is minus 4 into 28. Yeah, that's correct. And this is plus 1. So it is congruent to this 0 mod 4. So this is congruent to 1 mod 4. So then the ring of integers of q root minus 1, 1, 1 is z1 plus root minus 1, 1, 1 by 2. And the discriminant is 1, 1, 1 plus root minus 1, 1, 1 by 2, 1, 1 minus root minus 1, 1, 1 by 2, the square of that. And that is your So it's simply minus 1, 1, 1. So that is, it's a simple calculation. So this minus 1, 1 is a fundamental discriminant. And so this is the discriminant of the number field, and it is also the discriminant of the ring of integers. So this is the discriminant of this ring of integer. We anyway know if D is congruent to 1 mod 4, then the discriminant is D basically. So, but this formula is derived using this. So I just worked out the detail. Next case, you have minus 1, 1, 3 is minus 1, 1, 12, minus 1. So again, this is minus 4 into 28 minus 1. Yeah. So this is minus 1 mod 4, which is 3 mod 4. So for 2 and 3 mod 4, the ring of integer of the ring of integer of is z 1, 1, 3 is z root minus 1, 1, 3 z root d. This d is 2 or 3 mod 4. And the discriminant of u root minus 1, 1, 3 is equal to is equal to determinant of this. So this is 4 times d, and so it is determinant of 1, 1 square root of minus 1, 1, 3, 1 minus square root of minus 1, 1, 3 square. So minus 2 times square root of minus 1, 1, 3 square. So 4 into minus 1, 1, 3. So it is yeah, minus 4, 5, 2. So that is it. So this is, and the answer is minus 4, 5, 2. And here answer is minus 4, 5, 2. So next problem is, consider the set x, y, z and zq, x to the power 8 plus y to the power equal to z to the power 8. Then which of the following is true? Okay. Z101 is in S, 9, 15, 46 is in S, 33, 76, 45 is in S, and the last one is the solution in Z cube says that x, y, z not equal to 0. Intersection S is empty, that means there is no solution with x, y. Every solution is x, y, z equal to 0. So clearly the first one is true. And so is the last one. This is why the last one is true. So this is true because, you know, if you have a solution a to the power 8 plus b to the power 8 equal to c to the power 8, then you put a prime equal to a square, b prime equal to b square, and c prime equal to c square. Then you get a prime square plus a prime 4 plus b prime 4 equal to c prime 4. And that we just proved, or at least we have stated clearly, that it follows from 1 is not a congruent number. That this is a Fermat plus theorem equal to 4 case. This will imply a prime, b prime, C prime equal to 0, which will imply that ABC equals. Right? This is the whole chain number. Okay, so this is kind of the chain number. So this is not possible, and so you don't even need to check. These are some none of the coordinates are 0. Here it's of course very easy because this third coordinate has to be greater than this, so that's not possible. But yeah, you don't need to really check it. You don't need to worry. I mean, yeah, here it's very easy. But otherwise, also any three numbers you give, however carefully chosen, but at least one of them is non-zero. If all three are non-zero, then it's not a solution. So simply, right? Okay, so next question is what if you change the set S to S1 equal to XYZ and ZQ, so that x to the power 4 plus y to the power 4 equal to z to the power 4. Then directly, and then you give options like this. One is 101, or let's say minus 101. Another is this, and then there are other two options, or all three are non-zero. Then again, you can conclude because this is only solution to this is ABC, all three XYZ. This happens if XYZ equal to 0, right? That's what we proved some time back. I'm not going there because we are going to discuss this again. So this is the n equal to 4 case of Fermat's theorem, right? So this is directly n equal to 4 case of Fermat's theorem. Last theorem. And we are going to discuss the proof in full detail, but it essentially follows from essentially follows from the proof of one is not a congruent. Okay. Okay, so then there is some exercise on congruent numbers. Which of the following are not congruent numbers? Yeah, so first one is not a congruent number. The second is 2 is not a congruent. So 1, okay, so the options given are 1, 2, 5, 6, 7, 15, 21. So let's go through one by one. First is 1. Then we know 1 is not a congruent number. This is one of the theorem we have proven, right? The second is 2. 2 is not a congruent number. This we have given as an exercise. Similar to 1, you can prove. Similarly, 3 also you can prove is not a congruent number, as I have stated. What about 5? 5 is a congruent number, we have shown. And in fact, if you recall, so 5 and 7, we have this matrices. 5 and 7, we have this matrices. We recall here. So 5, we have this matrix. Sorry, 5, we have this triangle. 20 by 3, 3 by 2, 41 by 6. And this area is half into 20 by 3, 3 by 2, which is 5. And 20 by 3 square plus 3 by 2 square is 41 by 6 square. And we have 24 by 5 and 35 by 12. And half into 24 by 5 and 35 by 12 is 7. And 24 by 5 square plus 35 by 12 square is 7 by 60 squared. So we have seen that. And we have seen that 1 is not a congruent number. So that was answer to one of the questions. And we have also seen that, or assumed that this is x to the power 4 plus 7 to the power 4 plus 2 to the power 4 equal to y squared with no solution. And that implies that x4 plus y4 equal to z4. With no non-trivial solution, any solution satisfies that product, at least one of them is 0. So the same happens here. Any solution satisfies at least one of them is 0. Okay, and so this was the exercise that 2 and 3 are not congruent numbers. So then we do two exercise. Yeah. So 2 is not a 5, it's not a 6, is a congruent number, is easy. 7 is a congruent number. Show you the triangle. Next is 25. So we know 15 square plus 8 square is 17. There's some identity, some trial and error method. So we know 15 square plus 8 square is 17 square. And half into 15 into 8 is 60. Right? So 60. So 15 square plus half 8 square is 17 square. And half into 15 into 8 is 15 into 4. Right? So 15 into 4, 60 is a congruent number. But 60 is a congruent number if and only if. So d square n is a congruent number if and only if n is a congruent number. So 15 is a congruent. And in fact, you can take 15 by 2 whole square plus 4 square is 17 by 2 whole square. From there also. Next is 21. So here there is this identity 7 square plus 24 square is 25. 7 square is 49 and 24 square is 4 into 12 square, which is 4 into 1 for 4. And they add up to 620. And what is half into 7 into 24? Half into 7 into 24 is 7 into 12. So that is 7 into 3 into 4, so 21 into 4. So 84 is a congruent number. And if 84 is a congruent number again, because 4 is a square, that implies 21 is a congruent. Okay. So 21 is also a congruent number. And we have 144 plus 25 is 169. So 144 is 12 square and 25 is 5 square. So that is 13 square. Right? 12 square plus 5 square. So this is nothing but 12 square. Right here. 12 square plus 5 square. 13 square. Yeah. And everything here. And half into 12 into 5 is 30. Okay. So 30 is a congruent. So here are some list we check, which is congruent number. So these were like, so you have to come up with some triangles and some identities in that include the congruent number. But something is not a congruent number like 1 and 2 needs a theoretical argument. And 1 I did, and 2 and 3 I've left to exercise. Okay. So, so one of the thing here, okay, so before we move into this, so we did some exercises. I want to do some errata here. Some errata. Yeah, so in one of the places in the classification of binary quadratic form to the reduced one, a equal to minus b, I said xy going to x plus y takes ax square minus axy plus cy square to ax square plus axy, a plus c y square. And that is not correct because, yeah, this will take ax square minus axy plus cy square to ax square plus axy plus cy square. Indeed, that is what we wanted to do. If this was a reduced form and this b, so mod a was mod b and this b, so b was minus a. So mod a was equal to mod b. And and b was possibly negative, so we just wanted to make b to be positive. So the choice was to make it to ax square plus axy plus cy square. And indeed, this goes by the transformation x going to x plus y and y. You can clearly see if we put x plus y here, then because here if you put x plus y and here if you put x plus y, then this is not a plus c, this ax, y and xy get cancelled, so it will actually be, this was incorrect and this is the correct one. There's this thing, and in a couple of places the English spelling of Brahmagupta is correct one is this BRAHMAGUPT. Some a couple of places. Somewhere it's correct. Okay, so let us come back. Now, to this Pythagorean triplet. So what we are discussing in congruent number, we are discussing two conditions. One is a square plus b square is c square, and second is half ab should be equal to n. Right? This is our condition. That half ab is equal to n, where a square plus b square is c square. So what is, so if you find um, so so a square plus b square is c square is like a formalized equation. We have noticed that for n greater equal to 3, fix n equal to 3, then x to the power n plus y to the power equal to z to the power n has only solution x, y, z in z cube such that satisfying x, y, z is 0, product of them is 0. But n equal to 2, a square plus b square equals c square, there are lots of such solutions. And the thing is, if a square plus b square, there are lots of such solutions. And why here, sorry, why we are suddenly talking about this? Because if we find, presumably, the one of the question I asked, what are the congruent number, and I'll discuss a bit more about it. But if you find all x, y, z, all ABC, so that a square plus b square equals c square, then you just collect half of AB, and you can always scale it down to make n to be an integer, right? So if you find all ABC, then such that a square plus b square equals c square, then you find all half of AB, and that is the answer to all congruent numbers, right? So I am going to discuss a bit more about it, but yeah, so that's why Pythagorean triplet is important here. And as I said, n equal to 2 is the only case where there, I mean, any other than n equal to 1, that where there are lots of solutions of this Pythagorean triplet. So we'll quickly recall this classification. One of the things is when you are studying Pythagorean triplet ABC, then we can assume that ABC are co-prime, no prime divides ABC, because if ABC is a Pythagorean triplet, then you have lambda A square plus lambda B square equal to lambda C square for all lambda n, if and only if A square plus B square equals C square, right? So ABC is a Pythagorean triplet if and only if lambda A, lambda B, lambda C is a Pythagorean triplet. So without loss of generality, we may assume that ABC are co-prime triplets. Okay. So recall ABC in NQ is a Pythagorean triple if A square plus B square equals C square, and we call a Pythagorean triple to be primitive if ABC has no common prime factors, or equivalently, any two of them have GCD equal to 1. If any two of them have GCD 1, then it cannot divide then the GCD of the third one with, so then they cannot have any prime factor. So let's say A and B have GCD 1, then B and C, if the GCD is D, then D will divide A also. That will mean D divides A and B, which is the contradiction. Similarly, C and A, if D divides C and A, then D will divide B also. So that means again D will divide A and B, which is the contradiction. So if any two of them have GCD 1, then mutually any two fixed of them, of the three ABC, if we assume they're GCD 1, then it automatically means they're pairwise couplet. And so equivalently, you assume that to be primitive if they have no common parent factors. So what are all Pythagorean primitive triple? That is the question. If ABC is a primitive Pythagorean triple, then one of A and B must be even and the other one must be odd. Because if both are even, then 2 divides A and 2 divides B, and then 2 divides C also. C also becomes even, so then their GCD is not 1. On the other hand, both cannot be odd also, because if A and B is odd, then A square is odd and B square is odd. So A square plus B square is even, but A square plus B square is even. But C square, being a square, is mod 4. It is either 0 or 1 mod 4. But since A and B are odd, then A square plus B square will always be. If both are odd, it will be 1 mod 4. So that will be a contradiction. So exactly one of them has to be even, another one has to be odd. So let's say A is even and B is odd, then C is also odd, by the way. So then the classification is A is always of the form 2KL, B is of the form k square minus L square, and C is of the form k square plus L square, where k, L are natural number, k, L, k is greater than L greater than 0, k, L and co-prime, and k, L and have different value. Okay, so this is the classification. So you plug in, put all such k and L, and that will give you all ABC. And if you know all ABC, then you know presently half of AB. All ABC such that A square plus B square equals C square are given by, just take any KL such that K greater than L greater than 0, KL are co-prime and KL are different priority and KL are natural numbers. And then you just put A equal to 2KL, B equal to K square minus A square, and C equal to K square plus A square. Clearly, this is a Pythagorean triple. We can check and so prove indeed 2KL, K square minus L square, and K square plus L square is a Pythagorean triple, because 2KL whole square plus K square minus L square is K square plus L square whole square, right? A minus B. Yeah, so this is just easy to check. You check. And they're a primitive triple. So you also have to check why did you get a primitive triple. Because if D divides K square minus L square and D divides K square plus L square, then D divides by summing them to K square and D divides to L square. But K square minus L square and K square plus L square are both odd, right? So A is even, then B is odd, so C is also odd. Exactly one of them can be even. Because of one, both cannot be even because GCD is 1, and considering mod 4 and A square plus B square is C square, A and B both cannot be odd. So exactly one of them is even, another is odd. So C is also odd. So K square minus L square and K square plus B square are both odd. So if D divides an odd numbers, and the D is odd. Okay, so D is odd and D divides 2K square, so D cannot divide 2. So D divides K square and D divides L square, so D divides K and D divides L, so D is 1. Okay, so this is indeed a primitive Pythagorean triple. So this way, if you give this formula, we are actually getting Pythagorean. And the proof is easy, and we'll give the algebraic proof, there is geometric proof. So next time we'll see this proof and we'll see how that is relevant to congruent number. Thank you.